Don't worry about it, I'll get it. Sure you don't need any help? All right.
Thank you.
Have a good one.
You too.
Okay. We'll wait for Dalton to get back. There you are. All right. So, today we're going to be getting into probability, which we've already talked about probability once before, a little bit, towards the beginning of the semester when we did the coin flip experiment. So just to remind you what that was, is we flipped a coin 50 times, and then we also had somebody just make up 50 coin flips and write them down, and we compared the results. And so the actual coin flip and the fake coin flip results didn't really look the same. In fact, they were different enough that I was able to predict which one was which. Okay? So, we have to keep in mind that probability doesn't always work the way that we assume it does. Let's take a closer look at probability today. So I brought some dice with me today. So I've got a normal 6-sided die here. Now to start us off, if I wanted to roll a 3, you just roll it once and get that 3. What is the probability that I'd get it? 1 in 6, yeah. Now the reason we say it's 1 in 6 is because on this die, there is only one number that is favorable. Again, I want to roll a 3, well there's only one 3 on here. And then the total number of different possibilities on here, well there's 6 different faces, so there's 6 different numbers. There's 6 possibilities. This is very much like what we were doing on our exam when we did the question about the mid-size phone carrier who had complaints, and it listed all the complaints in that chart, and we had to find the percent. Well, it's a part out of a whole, right? Well, the part is favorable outcomes, and the whole is the whole amount of outcomes possible, which also means that we can turn this into a percent. So 1 out of 6, 1 divided by 6, and then times 100, we get 16 point, let's say 7%. Okay? So what we can say about this is, yeah, I can roll this die. The possibility of getting a 6 on my first roll is 1 in 6. I didn't get it, but I can keep rolling it. Still didn't get it. Let's try to get that 6. Come on. Oh, there we go. So it'll take about 6 rolls for me to get that 6. But I mean, at the same time, I could just get it on the first roll. So, does this tell us exactly what's going to happen? No. This does not tell us that we need to roll this 6 times and we'll get a 6 exactly once. In fact, we could roll this a bunch of times and get the 6 every time. We could roll this and never get a 6. Okay? What this is telling us, though, is that as we roll this over time, and we just keep rolling it and rolling it and rolling it, this is how much we can expect to see a 6 come up. So over however many rolls we do, about 16 or 17% of them are going to come up as 6. Again, it's not guaranteed that that will happen. We could roll it 100 times. We could roll it 1,000 times or 1,000,000 times. And we might never get a 6 to come up. But as we keep rolling it, it's likely that about 16 or 17% of the rolls are going to be a 6. Does that make sense? Okay. So let's try some other examples of this. How about instead of just a single number, we could look for multiple numbers, like what's the probability of rolling an even number? Yeah, 50%. Half of them are even numbers and half of them are odd numbers, so probability there would be half, or 50%. Okay, so what's the probability of rolling a 1 or a 2? Well, yeah, it's 2 out of 6. We have 2 possibilities there. So it's not 2/3, it's 1/3, yeah. Or if we put that into a percent, that'd be 33.3%. Okay? So simple probability, just how many outcomes are favorable versus how many outcomes total. Any questions? Okay, let's complicate things a little bit then. Okay, so I've got a different type of die here. This is an 8-sided die. This is what we call a D8. This, of course, would be a D6. So let's say I want to roll a 2 on this one and a 4 on this one. Okay? Well, what would be the probability, just this one alone, of rolling a 2? Nor this. Yeah, 1 in 6. So for our D6, we have a 1 in 6 chance, right? Okay. So then what would be the probability of rolling a 4 on my D8? 1 in 8, yeah. Okay. Now let's see, how would we put these together? How would we make this one single probability? See, that's what a lot of people would think. In fact, I've had that answer every single class period today. So you'd think, well, I've got 6 possibilities here and 8 possibilities here. So together that'd be how many possibilities? 14 possibilities, yeah. So maybe it's 2 and 14, so 1 out of 7. It's not actually quite working that way. Because we've got to take into consideration that these are kind of affecting each other a little bit. Think about it this way. This one, the possibilities are 1, 2, 3, 4, 5, and 6. This one has possibilities 1, 2, 3, 4, 5, 6, 7, 8, right? So let's say that I roll this one and I get a 1. Okay? Then I roll this one. Now, without looking at what I get on that, if I get a 1 on here, this 1 could be paired up with any of these possibilities, right? I could roll this and I could get a 1, or a 2, or a 3, or a 4, so on and so forth. So if I roll a 1 on this die, there are 8 possible outcomes, just for if I roll a 1 on this die, right? Same thing, if I roll a 2 on this die, there are 8 possible outcomes for this die as well.
How are there 8 possible outcomes on the one on the left?
On this one?
Is there?
How are there?
Is there?
Because there's 8 sides.
Well, so I thought you were talking about the left one.
No. So this one, if I roll a 1 on this one, and then I roll this one, there's 8 different things that could happen. If I roll a 2 on this one, and then roll this one, there's, again, 8 different things that could happen. So there's 8 here, 8 here, 8 here, 8 here, 8 here, 8 here. So each of these faces has 8 different things that could happen after I roll it. In other words, there's 6 possibilities here. Each of them has 8, so it's 6 times 8. So how many possible outcomes are there? 48. Which brings us back to our probabilities. If we want to know the total probability here, we multiply these two probabilities together. So 1/6 times 1/8, what's 1 times 1? 1. 6 times 8? 48. In other words, there is only one possible way for me to roll a 2 on this one and a 4 on this one. And how many outcomes are there total? 48. So it's a 1 in 48 chance. Does that make sense while we're multiplying these?
Yes, sir.
Okay, good. All right. So what if I had these? These are called percentile dice. There's 10 faces on each of these die, but they're the same die, which is with different numbers. So for instance, if I roll this, this is a 21%. Okay? So, think about it. Let's say I want to roll a 56%. Okay? Well, how many different 56s are there? There's only one. There's a 50 and there's a 6. And there's only one way to make them go together. And it's out of how many different possibilities? Nope. It's out of a percent. Remember, both of these are 10. So it's a 1 out of 10 for this one, and a 1 out of 10 for this one. So 1 times 1 is 1. 10 times 10 is 100. Again, it's a percent die. So there's only one way to get each of these combinations out of 100. So 27, there's a 1 in 100 chance of getting a 27. 29, 3, so on and so forth. Again, when we have multiple things going on, we need to multiply those probabilities together to get the total probability. Any questions? Okay. Now, I meant to also bring a deck of cards today, but I forgot them. We're just going to have to kind of pretend. So let's say I've got a deck of cards. How many cards are in a standard deck? 52. And from this deck, I want to randomly select a card, and I want to get a club. Any of the clubs. It can be a face card, it can be a number card, just as long as it's a club. So how many clubs are there?
Oh, no, there's not one.
How many cards in each suit?
Yeah.
13. You have
Yeah.
1 for the ace, all the way up to 10, and then you have Jack, King, Queen, so 13. So it's it's a 13 in 52 chance, or that actually reduces to a 1 in 4 chance, so 25%. So you got a 25% chance of pulling a club out of that deck. Now let's say I want to do it again and try to get another club. So let's say I got the club the first time and I want to do it again and get it. What's the probability now? Good, 12 and 51. Because I've taken a card out, right? And not only was it a club, which makes it 12 now, but it's also just a regular card, so it makes sense that it's 51. Okay? Maybe I get it and I want to do it again. What is it now? 1150, yeah. And it'll continue like this as I pull cards out. All the way down until we get to 1 in 40. Okay? Now, as I multiply these probabilities together, do you think it's going to become more likely that I get a club or less likely?
Well, I would say the same.
Well, okay, let's check.
Um,
Because that's a good, what do you call it, hypothesis.
yeah,
You should always test your hypotheses. So, this first time, I had a 25% chance, and now I need to multiply this times this to get my new percent. So, let's see, 13 times 12 is 156, and 52 times 51 is 2,652, so let's see what the percent is there. 156 divided by 2,652. This now becomes a 5.9% chance. Let's do the next one. So 156 times 11, and then 50 times 2,652. So then find the percent chance there, and this one is a 1.3% chance. So as we can see, as we keep going on and we are pulling cards out of here, the chance for me to get another club is dwindling each time.
I think you seem right.
Well, here's why. It's not that I'm trying to pull the club, it's that I'm trying to pull the club again and again and again and again.
Okay. Back to back.
Yeah, so, yeah, I might pull a club the first time. Got a 1 in 4 chance to do that. But to do it again is a lot less likely because I'm probably going to get one of those other cards. A heart, a spade, or a diamond. And as we keep doing this, my chance dwindles more and more and more. It's less and less likely to happen. So, yeah, how likely is it for me to pull a club the first time? Again, it's a 25% chance, pretty good chance. How likely is it that I pull the entire club suite out of the deck one at a time, just randomly? Oh, it's almost impossible. Okay. So, I want to point something out about this. Notice that what we're doing here, when we're multiplying these, I've got 13, 12, 11, 10, 9, all the way down to 1, and I'm multiplying all those. Same thing on the bottom, I got 52, multiplying all the way down. This one stops at 40. Okay? There's actually a name for this, and that is a factorial. So you might see something like 4 with an exclamation point. This is 4 factorial. What this means is we're going to do 1 times 2 times 3 times 4. Just like we have up here. So this up here, the top part of our probability here would be 13 factorial. And then the bottom part would be, well, 52 factorial, or 52 minus the 13 factorial. Okay? So factorials are actually quite good at coming up with probabilities and, in particular, outcomes. So let me give you an example of that. Think about your locker back in high school. So your locker had a dial on it probably, and so you turn that dial to particular numbers to put in a code, and if you get the right code, you open it up, right? So there has to be a certain amount of codes that you can put in on there. There's not an infinite amount. There's only a certain amount of ways that you can put a code in. How many codes?
A lot.
Oh yeah, definitely a lot, I'd hope. Uh, so, let's think about it. How many numbers were on that dial, if you remember? It's 50 or 60. Sometimes they have 100. But I've seen a lot of them that have 60. So a dial with 60 numbers. And then how many numbers were in your code? 3. It's pretty typical. Okay, essentially we're going to set this up to find how many different possibilities there were the same way we did this. But there is a general way to do it. We don't have to kind of think about it and like, okay, figure out where do we start and where do we end. No, there's a very easy way to do it, and it's called a permutation. Instead of trying to work through this and figure it out, permutation tells us that if we're doing something where order matters, so in this case order does absolutely matter because a code has to be put in a certain way, right? Has to be put in a certain order. That we can use the formula n permutation r equals n factorial over n minus r factorial. So this is the general form, and this is what you want to use when you're trying to figure one of these things out. Again, I was just showing you this so that you understand where it comes from. Okay? So we got to figure out what n and r are. Okay, so n is the number of things that we're trying to order. So how many things are there out there in this pool that we can pull from and put into our code? Well, that would be our dial, wouldn't it? So we have 60 different things that we can pull from. R is the slots that we're going to put them into. Remember, this is order matters. So we're going to put these numbers into these slots in a particular order. Well, how many slots do we have? We've got 3 slots in our code. So we can use this information, plug it into here to see how good your locker was. How many different codes were possible on that locker. So we've got 60 P3 equals 60 factorial over 60 minus 3 factorial. Let's see what happens. Of course, first thing we need to do is parentheses. So 60 minus 3 is going to give us what? 57, good. So now we have 60 factorial over 57 factorial. Well, factorial, like we said, is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. We've got to do that all the way to 60, and the same thing for 57. There's got to be an easier way. And there is. So, remember, it is actually like that. 1 times 2 times 3 times 4, so on and so forth, until we get to 60. Same thing for 57, it's just that 57 stops at 57. Okay. So what we have here is a fraction. And what can we do when we have a fraction that has the same number on top and bottom? In other words, if I had something like 3/6, 3 and 6 can both be divided by the same number, right? They can both be divided by 3. We can reduce that. It's the same thing here. Essentially, both these can be divided by 1. They can be divided by 2. They can be divided by 3. Anything that matches on top and bottom cancels. And so since these have a lot of similar things, we can cancel all those numbers all the way up to 57. And then we only have a few left. So 60, and then take away everything but 57, we have now just 58 times 59 times 60. Does that make sense? Okay. So instead of having to multiply all those numbers, we can just multiply these three. So 58 times 59 times 60 gives us, let's see, 205,320. And
always be, those two numbers always be that close?
I mean, no, and in fact, that is a good question. And that's going to get into what we're about to go over. So this is the number of possible combinations on that locker. 205,320. So that's how many combinations are on there. And so we can say that it's relatively secure, because if we were to just walk up to a locker and put one combination in, we have a 1 in 205,320 chance of getting that combination right. It's not a great chance. Now then, is it the most secure thing in the world? No. In fact, people who are really good at cracking codes could probably crack this in a few hours. A computer could do this in a few minutes. Okay? In fact, there are actually these machines that you can put on a dial like that, and they'll test out the combinations. And it'll just go through all these different combinations and finally figure it out. And it'll take a few minutes to get that many. So this isn't actually very secure. So what do we do to make this more secure? Well, it's like you were talking about. We need to spread this out a little bit more. Okay? So, we can either increase the n, or we can increase the r, or we can do both. But let's see what has more effect, because one of these actually does have a lot more effect on the number of possibilities than the other. So which do you think it is? Should we increase the size of our dial, or should we increase the size of our code to get a better security? I mean, yeah, if you increase both of them, then for sure the security would increase. But which one matters more, the size of the dial or the size of the code? What do you think?
You would think the size of the dial. I feel like
Very good, yeah. You would think it's the size of the dial. Let's go ahead and check and see what happens. So let's increase the size of our dial. Let's multiply it by 10. So instead of 60 numbers, there's 600 numbers. That sounds like it'd be very secure. So 600 P3, so still a 3-number code. And I won't go through the whole calculation. I'll just enter it into my calculator.
so that it has that exclamation point.
It has more than that. If you go to math button, there's a whole bunch of different formulas and things in it. So hit math, then go over to probability, and we have permutations, combinations, which we'll get to on Friday, and the factorial button. But we just need the permutation right now. So 600 for our n, and 3 for our r. And there's our number of combinations, or I should say permutations. So in this case, this lock would have, oh my gosh, it's a lot. Let me write it down first. So it'd have 214,921,200 different codes that you could put in. And of course, if you put that under 1, that's the chance of getting the right code the first time. Okay, so let's compare that to if we increased our code size. So just like we multiplied this by 10 to get 600, we're going to multiply 3 by 10 to get 30. Now, a 30-character code is kind of big, but there's a lot less distance between 3 and 30 than there is from 60 and 600. You know, this we increased this a whole lot, and we got this. This we haven't increased quite as much as we did this one. So let's see what happens. So same thing, but instead we have 60 and 30. Ooh. This comes out to be 3.137 times 10 to the 49th power. Yeah. So if you're familiar with scientific notation, you know that this means that to take this from this type of number to a regular number, would move this decimal this direction 49 times. That is a lot. That is an astronomically huge number. It dwarfs this number by quite a bit. So yeah, increasing the size of that dial does increase the security, but nowhere close to as much as if we increase the size of that code. In fact, let's just increase the size of the code a little bit. Let's make it 6 instead of 3, so double it. So go back to our calculator here. So 60 on our dial and 6 on our code. And we still have one of these huge numbers. I mean, a 6-digit code is pretty easy to memorize, but this is 3.6 times 10 to the 10th. I could actually write that. Yeah. Let's see, that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. Huge.
This wouldn't work with the alphabet, would it?
Oh, absolutely, yeah. So how many?
26 letters?
26 letters. And how big would your code be? However big you want, just guess.
8.
8, okay. So, again, we have 24 things to choose from. And we're going to use an 8-digit code. Make this a little bit easier to see.
Is it 24 letters? Or?
I'm sorry, 26.
Yeah.
Pretty good. And in fact, what you brought up just now with the letters, think about your passwords on internet. Okay? What do they want you to put into your password? They always want specific things. What are those things?
No spaces, at least 7 characters.
At least 7 characters. What else? It's got to have uppercase.
Something.
It's got to have numbers. It's got to have special characters.
Yeah.
Okay, so it's got to have all these different types of things in it. But it has to be 7 characters. Okay? Well, them making sure that you have not just letters, but also numbers and symbols and capitals, is that increasing the size of the dial or the size of the code? Size of the dial, yeah. They're increasing the end. They're increasing this number. When increasing this number has a lot more effect. Now, what they're going for there in making sure that you have at least 7 characters is, okay, it's going to be a decently hard code to crack. But making that password just a little bit longer dwarfs anything that you have to put in there with special characters and letters and numbers and things. So the guy who came up with that standard, he's a mathematician. I think he came up with it in the 80s. And he realized later on in his life that that was actually not what he should have done. He should have made sure that people have like 10 character passwords at least, instead of requiring all these numbers and things, because it doesn't actually increase the security that much to have those. Computers, they look at things like an exclamation point or a capital A, and it's no different to that computer than any other character. You know, it just has more that it has to draw from. But if you make a really long password, then that computer has to sit there and go through all the characters for each one of those numbers in your password, and it takes it a much longer time to get through. In fact, a good password will take a computer a millennia to get through.
How long is the millennia again?
1,000 years. Okay, any questions? All right, then I think that will do it for today. So remember that you have a test in Ms. Lamar's class tomorrow. How that? So be sure to study for that.
Can you start teaching that class?
No.
Yeah, you just a little bit better explain.
I think I got my hands full with this one.
Yeah, probably. She's just, it's so hard to learn with her sometimes.
Well, everybody has a different way of teaching, and that's why we've paired like this, so that if you don't get the stuff in her class, hopefully you'll be able to get it in my class. So she's teaching you more of the college level stuff, and I'm teaching you more of the little fine nitty-gritty basic stuff. Alright, but I will see y'all on Friday. I hope you have a good one.
You too.